In this lecture, we're going to talk about rectangular frameworks, and we're going to define what we mean by a rigid rectangular framework, and we're going to see a wonderful theorem that tells us about rigidity, and we're going to apply this principle or concept of a rigid framework to secondary RNA structure. So here's an example of a rectangular framework, or in graph theory, it's sometimes called a grid graph. We saw an example of a grid graph earlier when we looked at this graph. So in graph theory, usually vertices do not have a fixed position and edges usually do not have a fixed length. But a grid graph, or a rectangular framework, as they're called in computational geometry, are different. In a grid graph, you do have positions which are fixed. In this setting, we're allowing for additional edges to be placed in our graph. We're allowing for edges to be placed on what we might call the diagonal, and we will call these additional edges braces. The graph on the right is not rigid. As you can see, it can move without disconnecting the graph. However, as we will see, if we place braces at strategic points, then the graph will become rigid. Just randomly placing braces, however, is not sufficient to make the grid graph rigid. For example, on the right, we have braces placed in some of the rectangles, but as the drawing indicates, this is still not a rigid structure. So the question is, where do we place these braces in order to make the entire framework rigid? Fortunately, we have an absolutely wonderful theorem that can tell us whether or not a framework is rigid. First, we have to construct what's called the associated bipartite graph. So we're going to label each row with u sub I. In this case, there are 4 rows, so we have u sub 1, u sub 2, u sub 3, and u sub 4. We're going to label each column with a v, v1, v2, v3, v4, and v5. Now these are the vertices of our bipartite graph. We'll put all the u's in one partite set, all the v's in the other partite set. Now, if there is a brace in the ith row, jth column, then u sub I is adjacent to v sub j. For example, look at u3. There's only one brace in the 3rd row. That brace is in the 3rd column. So u sub 3 is adjacent to v sub 3. And that's its only adjacency. Now that we have constructed the associated bipartite graph, we look and see whether or not it's connected. You can see in this example that the associated bipartite graph is not connected. There is no path from u4 to the other vertices except to v4 and v5. So the corresponding framework is not rigid. However, you could look at the associated bipartite graph and determine what edge you would need. And there are different possible choices, but you could find an edge that you could place in the associated bipartite graph to make it connected, and that tells you where to put the brace in the framework. This is theorem 1.4.1 in your text. And this theorem says, if you have a rectangular framework, it's rigid if and only if its associated bipartite graph is connected. For more examples, you can see pages 26 and 27 in your text. Now there's quite a bit of research available on the rigidity of protein structures. Mainly, as I mentioned before, this is in the realm of computational geometry, or computational geometry applied to protein structures. However, there's very little that can be found on the rigidity of RNA structures. So we should return to the RAG database and explore rigidity of secondary RNA structures. So here was our explanation of how to obtain the line graph of the dual graph, which was a representation of secondary RNA structure. Now, when we obtain the line graph of the dual graph, we don't necessarily obtain a rectangular framework. However, we do get C4s, or cycles on length 4. So we'll pose the question, do all the cycles of length 4 have a brace? We see in this example, they do. Since both of the cycles of length 4 are both rectangles, a cycle of length 4 is a rectangle, since they both have a brace, let's say that this secondary RNA structure is rigid, and use this to prompt the following definition. We'll say that a secondary RNA structure is rigid if every rectangle in the line graph representation of its dual graph has a brace. So this concludes this video, where we saw some examples of rectangular frameworks, which are sometimes called grid graphs. We defined rigidity of a rectangular framework, and we found a wonderful theorem that helps us determine if a framework is rigid. We use these principles to motivate the definition of what we mean by rigidity of a secondary RNA structure.